Okay, we're going to learn how to do the impossible. We're going to learn how to count atoms. And so atoms are these incredibly tiny particles, right, that make up all of matter. And you might think an atom is too small to weigh, but you would be, well, sort of wrong, actually. Individual atoms are extremely hard to weigh, but we have figured out ways to do it, no pun intended. In fact, if you look at the periodic table and you want to learn how to count any kind of atom, all you need to do is to find the element on the periodic table. So if you're interested in carbon, you would look for C, and you would see two numbers above and below, and I'm going to teach you what those two numbers mean. And I think we've already talked about the numbers above and below, actually, so this is sort of a recap. The number above is the atomic number, and that is the number of protons in the nucleus of each atom. And that's also the number of electrons for the neutral atoms. And the number below is actually the atomic mass, or the atomic weight, or the relative atomic mass, or whatever you want to call it. And it is the average mass of all the isotopes. And so remember that some atoms can have different numbers of neutrons. And although chemically they're pretty much identical, the fact is they have a slightly different mass. And that 12.01 actually is the average of sort of 98%, 98.9% carbon-12, and about 1.1% carbon-13. And that gives you 12.01. But it also gives us a way to count, believe it or not, because it turns out that on average, one atom of carbon weighs 12.01 AMU, or just U for short. And so if you were able to weigh out an AMU of carbon, well, actually, you couldn't weigh out an AMU of carbon, but if you weighed out 12.01 AMU of carbon atoms, you would have weighed out exactly one carbon atom. So that is pretty awesome. And we can figure out how much any atom weighs. So for instance, if we go to our friend chlorine, and above chlorine, I believe we see a 17, and below it, we see the important number here, 35.45. And so what that means is that if we want to have one atom of chlorine, on average, it's going to weigh 35.45 atomic mass units, or just U for short. And so that gives us a way to count by weighing. And we often count very small things by weighing. So for instance, if you have a 1 cent piece and you take it to the bank, right, they might be able to count 1 or 2 or 3 pennies. But if you've got 25 1 cent pieces, right, you would probably wrap it up in a roll, and you would go ahead and you would weigh the roll in the bank, and the bank knows how heavy 25 pennies weigh. And so of course, counting by counting is for, well, people who have way too much time, let's put it that way. Most people practice counting by weighing. So let's learn how we can count atoms by weighing. So going back to our chlorine again, so we know that, one atom of chlorine weighs 35.45 atomic mass units of chlorine. And it turns out that there is another really cool connection with this number, and let me tell you what it is. And it turns out if you take that number of grams and you weigh out 35.45 grams of chlorine, you have actually weighed out 6.022 times 10 to the 23 atoms of chlorine. So, wow, okay, that's kind of a very large number, right? 6.022 times 10 to the 23. And it is a massive number. Let me give you an example of how massive that may be. So this is a figure right out of our textbook. So this is 6.02 times 10 to the 23. And wow, okay, so here we are in the fifth zero here. So this is your average tuition. So about $8,000 or $9,000 a year for Shawnee State. The population of Earth is in the trillions. Is it? No, it's not. It's in the billions. And so we would go out here. The distance from the Earth to the Sun is about here. So the age of the Earth in seconds. And very, very roughly, I always like to think that this number is approximately the number of stars in the entire universe. So that's pretty cool. And you might think, wow, there's a lot of stars in the universe. But you would be right. But in chemistry, we are used to numbers that massive. So for instance, if I had my nice cup of tea, and here is a very delightful looking cup of tea with some tasty biscuits or cookies on the side, and if I count the number of atoms in my cup of tea, there are on the order of about 6 times 10 to the 23 atoms in there. So that's pretty amazing. There's the same number of atoms in my cup of tea as there are stars in the entire universe. So that is a massive number. You might be interested to know that if we go back to, say, our carbon example, and we had that number on the bottom, which we said is the number of atomic mass units that a single atom of carbon weighs. And then if we weigh out that same number in grams, 12.01 grams of carbon, then we have 6.022 times 10 to the 23 atoms of carbon. So, wow, that's that same number again. So whenever we weigh out this number underneath in grams, then we have weighed out 6 times 10 to the 23 atoms of carbon. Just to give you an example, if you counted carbon atoms about 1,000 a second, you would be dead before you could get up to a number this big. You might say, well, it's okay, I'll have kids, and I'll tell my kids to count 1,000 atoms a second for the rest of their life, because they're going to be stuck indoors for the rest of their life if COVID-19 continues, and they would be dead long before they would finish the counting of atoms in your cup of tea. So we have that mind-bogglingly huge number that is actually quite easy to weigh out, because 12 grams of carbon can be weighed out in about 20 seconds or so if you're a little bit sloppy, and you've essentially counted a number that is equivalent to the number of the number of stars in the entire universe. Wow. And perhaps you're wondering, is it a coincidence? And it turns out, no, it is not. In fact, if you look at that number under lithium, then what that means is if you weigh out 6.941 grams of lithium, you have weighed out exactly that number, 6.022 times 10 to the 23 atoms of lithium. So that's pretty cool. And if you take something like zinc, there we go. So zinc has 65.39 written underneath of it. And if you weigh out 65.39 grams of zinc, which is quite good for the common cold actually, then you have weighed out exactly 6.022 times 10 to the 23 atoms of zinc. So it is very cool. So that periodic table is your best friend, because that number underneath each element is the average weight of each element. So titanium on average weighs 47.88 atomic mass units. And it also tells you that if you wanted to weigh out 47.88 grams of titanium, because you were a curious sort of person, you would actually be weighing out 6.022 times 10 to the 23 atoms of that element. Wow. And that number is a very famous number, so that is called Avogadro's number, after Avogadro, who actually did not discover the number, but he's such a cool dude, we decided to name the number after him. So we have lots of things, for instance, that have a special name. So when we have 2 of something, we refer to that normally as a pair. When we have 12 of something, we refer to it as a dozen. And if you're dealing with donuts, of course, one of the donuts could be small. And bakers have figured out that you better give people an extra donut. Otherwise, they'll complain about that one small one. That's a baker's dozen. 20 of something is called a score. So 3 score and 10 would be 70. And we buy our pencils in the science department in very small boxes. And they come in 144 in a box. They're golf pencils. And 144 is called a gross. And so it turns out that Avogadro's number is kind of like the chemist's dozen. And we have a name for Avogadro's number when we have this number. So when we have 6.022 times 10 to the 23 of something, we call it a mole. And we abbreviate that to just MOL. So if we go back to our carbon example, right? So carbon on our periodic table had a 12.01 underneath. And so that told us that if we took 12.01 grams of carbon, then we have counted out that mind-bogglingly huge number, 6 times 10 to the 23 atoms of carbon. And we can instead write that as a mole, because a mole is just a very big number. In fact, the number is so large, it scares most people, so we prefer to call it moles, because moles are cute and cuddly, as opposed to 6 times 10 to the 23. So here's a cute and cuddly mole, and he is our mascot, I suppose, in chemistry. So whenever we weigh out a mole's worth of something, it's just that number underneath the element in the periodic table. How cool is that? So we can go back to some conversion factors we looked at in chapter 1. So we now know that a mole of carbon is that very large number, 6 times 10 to the 23, and we can count out those atoms in a very simple way. We just weigh out 12.01 grams of carbon. And now we got two things that are equal to each other. So whenever we got two things that are equal to each other, we can divide one by the other. And if they're equal to each other, then that is essentially just the number 1. Or we can divide the second one by the first one. So we can write 1 mole of carbon weighs 12.01 grams, or 12.01 grams of carbon is equivalent to a mole. And these are our conversion factors. And the thing about conversion factors is that they're used to make conversions. So let's try conversion. So diamonds, it turns out, are pretty much just giant lumps of carbon. You can burn them. You can grill your hot dogs over top a diamond fire, a diamond grill. It's a very expensive way, by the way, to grill your hot dogs. I don't recommend it, but maybe you've got a giant lump of diamond that you are, well, what are you going to do with it, right? You're hungry. You can't eat diamond. Well, actually, you can, but it grinds down your teeth. And maybe you've got 5.48 grams of diamond, and you want to go ahead and you want to convert into moles. And so we know that the conversion factors we need are 12.01 grams, and that's equal to 1 mole of carbon. So we have to decide what goes on the top and what goes on the bottom. And you know what? If we put the grams of carbon on the bottom and we put the moles of carbon on the top, then we get something that gives us some nice unit conversion. So I can go ahead and move these things up. So I put the 12 grams on the bottom and I put the 1 mole on the top. And of course that gives us our unit cancellation. So those grams and those grams go the way of the dodo, and we're left with moles. And so we can go ahead and we can work this out. So how many moles of carbon are there in our very expensive diamond? We probably should pay slight attention to the significant figure rules. So since we're chemists, so at least we're studying chemistry, we have 3 sig figs there. We have 4 sig figs here. We have an exact number of significant figures here. So we're multiplying and dividing. So we keep 3 sig figs for the end of the day. And when I run this on my calculator, I get 0. So that initial 0 doesn't count as significant. 4, 5, 6. The next number is a 2, so when we round, we basically just lop that off. And oopsie, right, I'm supposed to write units next to that, so that would be moles of carbon. So we've converted our first grams to moles. Well done.